So, that said, he theorized that there was this gravitational constant. But he didn't actually figure it out before he died. And it wasn't until a little over 100 years later, 120, 130 years later, that a man named Henry Cavendish came along. Henry Cavendish was very wealthy, and he did a lot of things apparently. I've listened to some very respected physics teachers praise his work, and studied some of his work, but mostly what I was interested in was how he determined this gravitational constant.
Aren't we all?
Okay. Cavendish apparently had a lot of property, a lot of money, and he set up an experiment where, get rid of all this. Now let's go back to where we just have these two equations. They haven't figured out the big G yet. They do know the radius of Earth, though, because they knew the circumference. So they knew the radius of Earth, but they didn't know big G, and they didn't know the mass of Earth. Okay? So going back to Cavendish in 1798, Cavendish built this box, this wooden box on his property. Something like this. Okay? And in this box, there was a pulley with a rope leading outside the box, something like that, a little handle on it. And what hung from it was this thing called a torsion rod. Something like this. And on the ends of the rod were these large lead balls. And on the inside were these smaller lead balls. Something like this. Pulley right here. And he used lead because it's very massive, it's very dense. And he, apparently, according to the history, he knew that he had to get away from the box because his gravity, his mass, would affect the experiment. Assuming.
Okay, well, in the first part of Balls Out Physics, episode 2.0, Brian discussed weight, force, and mass. And now he's going to start delving into the gravitational equation, including how big G, the gravitational constant, was determined by Henry Cavendish in, 1798. Now, so far, he's done a passable job of describing the setup of the Cavendish experiment. We're going to correct a couple of errors that he made. You have to really understand how the Cavendish experiment is done to actually be able to describe how it was set up. Well, we've learned that Henry Cavendish was apparently rich and had a lot of land. Okay. We've also learned that he apparently has done some things in physics that Brian thinks he may have studied when he was in school, but the only one that really sticks out in his head is this particular experiment. Okay. And we've also gotten Brian to acknowledge the fact that the Earth has a known radius, which is interesting considering flat planes do not have a radius. In this case, a sphere has a radius because, of course, the Earth is a sphere. So let's cue up the music, listen to Brian struggle through the Cavendish experiment, and see how big G was calculated. Okay, now, so before we really get too deep into this, let's go ahead and review the Cavendish experiment. Now, in Cavendish, what he did was he basically had a large lead ball, and he had a small lead ball. Now, the large lead ball was fixed, and what he did was he measured the attraction between the large lead ball and the small lead ball. Now this lead ball here could move back and forth. So since this one was fixed, all the movement, all the force of the attraction was directed on this small ball. Now what he did to measure this force of gravitational attraction was that he had something called a torsion spring on this. And this torsion spring, which basically could rotate, could counter the force of attraction that went that way. And once this ball went into balance, this force equaled that force. So, and the way that he set it up was actually kind of interesting. Now, as you know, the Earth's gravity is constantly going in a downward direction at 9.81 meters per second squared. So, he didn't want the small balls affected by the gravity. So what he did was he hung them above the ground so that the downward acceleration of gravity affected both of the balls equally. And then what he did was basically set them up. Let's go ahead and put this over in a top drawing. So he's got his little balance beam here with the two small lead balls on it, and there's a wire right here in the middle. That's the torsion balance, and we'll get to that in a second. So the first thing that he did was he set it up at 90 degrees to the large balls. And he let this system go into equilibrium so that the small balls stayed perpendicular to the large balls. Then what he did was he rotated these large balls over towards the small ones, not quite touching them, but close. I think it was probably 4 or 5 inches away. Now the large balls weighed over 200 pounds. The small balls weighed, a matter of just a couple of pounds. So once they were in balance, what happened was the large balls in green here were fixed, and the small balls on the torsion balance were free to rotate back and forth like this. Okay? So the first thing that happened was these balls were attracted to the large balls. However, that attraction was countered by a wire right here that twisted. And when it got to the point that it twisted enough that the balls stayed in a stable position, somewhere balanced between the twist and the attraction to the large balls, this force right here equaled the force of attraction of the balls right there. And through mathematics, he was able to calculate what these forces were and therefore measure that force of attraction. Now that's the way that he set the experiment up. And as Brian mentioned, he didn't want his mass, the mass of his body, affecting this system in any way. So he basically set up a mirror right here and shined a light on it. And by measuring where the reflection was on a scale over here, he was able to determine how much this torsion wire swung. Let me show you a quick animation of that. Okay, so let's have a look at how Cavendish's experiment was actually set up. And this is a modern version of it. But basically what you have is right in the center, you see an inverted T that has two small gold balls on it. These are the small balls. And the thing that it's hanging from is the torsion scale. You see that there's a mirror, like a dental mirror, on that torsion scale, and there's a light source shining on it, reflecting off on a gauge, which is graduated there in the end. Now on the left, you will see the large balls being moved towards the small balls, decreasing the radius and increasing the gravitational attraction between them. Now watch what happens when they come together. You see how the balls are brought in and cause a deviation of the light. You also notice too that these balls are perpendicular, in a plane perpendicular to the plane of the acceleration of gravity.
Assuming that this is correct, that the force of gravity is, there's a force of gravity between any two masses, not just the Earth and us. All masses have a force of gravity on each other, or create a force of gravity on all other masses based on this equation and the proportion that Newton came up with. So he somehow set up some telescopes that went back to his house. Keep his house off the board, just assume his house is down here somewhere. So he could observe this experiment, and somehow he calculated big G from this. Okay. Well, when I started researching this, I said, okay, well, let's see some examples of a modern day torsion rod experiment that somebody's built that shows how this works. Well, I couldn't really find one.
Well, then apparently you didn't look very hard, because here's one right here. For example, here's just a basic search of YouTube for the Cavendish experiment, and there's a couple of examples right there, and of course the flat earth version trying to say it can't be done. Here's BM Furball Pancake Hero, a friend of mine, who's setting up a Cavendish experiment right in his apartment. And he's got it in a box here, as you see. He's used PVC pipe, and quite frankly, it's working. So as you see, he's got a torsion balance here made out of PVC pipe. It's got small weights on it. It's enclosed in a box to keep it away from air currents. It's got a laser with a graduated scale on it. And once he's got the torsion balance in equilibrium, with the large weights at 90 degrees, he can rotate them towards the small weights and get his readings. Okay, so the bottom line is that I find Mr. Mullen to be rather disingenuous when he says that he cannot find an example of a working Cavendish experiment. I spent 5 minutes on the internet and on YouTube, and I found dozens of examples of them, some even done by high school students in their garages. So that's just not an excuse. I'm sorry. But let's go ahead and continue.
And I'm thinking to myself, over 200 years later, we don't have models of this, or repeats of this experiment all over the place that determine big G.
We do.
It didn't make much sense to me.
You didn't look.
So I said, okay, well, going back through the history, let's assume that he did this somehow. He's a really smart guy, and we just haven't been able to get it to work again. Okay?
No, not okay.
So Cavendish determined big G through that torsion rod experiment. Okay? So he calculated it to be the value that we're still using, which is 6.67 408 times 10 to the negative 11 meters cubed over kilograms times seconds squared. Okay? He determined that from that experiment. Let's assume that's correct. So now he must have been really excited because he knows what this big G is. He knows what his mass is, or any other mass of an object on Earth. He knows what the radius of Earth is. So he can set these two equations equal to each other. He knows that weight and the force of gravity are equal. So what he did was, you can look this up. This is exactly how this was done. Weight, which is equal to mass times G, or the mass of the man or whatever object he's using. In my case, I'm going to say me, is equal to big G times the mass of the man times the mass of Earth divided by the radius of Earth squared. Now immediately, you can cancel the mass of the object, or me, out, because they're in the numerator on both sides. This is really mg over 1. Okay? And now, let's come up here. You can solve for the mass of Earth.
Yes, easily.
You can multiply the radius squared times both sides, and that comes over here. Cancels on this side. And then you can divide by big G. So you get me, and this is basic algebra here, is equal to little g, the acceleration due to gravity, or the rate at which things accelerate towards Earth, times the radius of Earth squared divided by big G. And that is how the mass of Earth is calculated. That is the mass that NASA had on their fact sheet, where I got all this information about the Earth's radius and the mass of Earth and everything.
Okay, so the fact that NASA has it on its fact sheet isn't all that important. It's on a lot of fact sheets. When people ask for what the mass of the Earth is, this is how it's calculated. You just did it. So what's the mystery here, Mr. Mullen?
For this problem. Okay. So I looked at this and I said, okay, that makes sense, but I still had the question in my mind saying, wait a second though, why can't we do this torsion rod experiment now? There's some. I looked into this more, and right now there's debate going on about what this big G actually is. Some people are arguing and saying it's different, and they're doing experiments on an atomic and a subatomic level where they're looking at particles with very powerful microscopes and observing how they're attracted to each other, which they say is because of gravity.
All right, first of all, no, I don't think that's how subatomic particles looked at by an electron microscope are attracted to each other. All right, there's charges involved and all sorts of other things. Second of all, Mr. Mullins, you are a liar, sir. This experiment is conducted on almost a daily basis, tens of thousands of times at universities throughout the world every year. Even a cursory look on YouTube shows that this experiment is done and gives reasonably good approximations of G. And it's done by amateurs, high school students, college kids, people doing it in their apartments in Korea, like my friend BM Furball Pancake Hero. They're coming up with reasonably close approximations of what G is, and considering the limitations of their equipment, that's pretty good. I cannot believe that somebody that actually studied physics on a university level like you is even questioning this. Why didn't you do this in your training? It seems like you barely even know who Cavendish is. Did you actually study any physics in your engineering degree?
Now, I can't go buy an electron microscope and do those experiments myself to check it because I don't have that much money. And I don't want to try to build a torsion rod experiment because from everything I read, it sounds like it's not going to work. So I'm also going to spend a lot of money on that. So I'm really questioning, this big G. How did they come up with that? But then I started to look at this algebraic expression that was written. Get rid of big G again.
I'm just going to reiterate. The apparatus that is being put together by Blake, BM Furball Pancake Hero over in Korea, consists of some cast iron weights that he bought at a sporting goods store, a little bit of PVC pipe. His torsion balance is piano wire, and he's using the brain God gave him between his ears to do the math. He's not a professional scientist. And if he can do it, Mr. Mullins, you could have done it. And you could have done it very cheaply, or you could have simply looked at YouTube and seen where other people had done it and looked at their results. So I'm finding your presentation that this is somehow in question or can't be done in modern times not only presumptuous, I find it offensive.
Say, well, what if they were so sure about this equation due to gravity, or this equation of gravity, that they were having trouble coming up with G, that they did something else to determine it? What if they did this? Or Cavendish did this? What if he said G is equal to the acceleration due to gravity, as he would have called it, times the radius of Earth squared times the mass, or divided by the mass of Earth. Of course, he doesn't have the mass of Earth, right? Well,
okay. Now, I swear to God, first of all, this equation, as you have written it, would work fine if you knew what the mass of the Earth was. But I think that what you're about to do is suggest that he made it up so that it would fit. And that, sir, is totally unacceptable.
It does have the radius of Earth. And at that time, they definitely knew how to calculate the volume of a sphere. The volume of a sphere is equal to 4/3 times pi times the radius squared, or cubed actually. In this case, it's the radius of Earth. So since they know the total volume of the Earth, they know that if they could figure out the average density of Earth, they could multiply that by this volume and get mass.
Yes, you easily could. However, what you're neglecting to look at, Mr. Mullins, is the entire purpose of the Cavendish experiment, which was to find the average density of the Earth. It was a great problem trying to calculate that at that time. By measuring G and coming up with a gravitational constant, he was able to accurately calculate the mass of the Earth. And with that, divide it by the volume of the Earth due to the known radius, and come up with an average density.
At the time they would have known the density of water and the density of sand, the density of ground rock, the density of iron, the density of gold, the density of silver, the density of all these things were already determined. And to determine the density of something, it's really just the mass per unit volume. For example, we'll call them rho. Call rho density. Rho water is equal to 1,000 kilograms per meter cubed. What that says is in 1 cubic meter, you have some.
Okay, I'm just going to kind of skip through this a little bit. Calculation of density is a relatively straightforward thing. You take the mass, you divide by the volume. Okay, we don't need to go over the mass of water, the mass of sand, the mass of iron, etc., etc., etc. We get the point here, Brian. The point of the entire Cavendish experiment was to find the average mass of the Earth. So let's go ahead and get to the meat of this. After going through this in excruciating detail, we see that the density of water is 1,000 kilograms per meter cubed. Soil and sand, 1,200 to 1,600 kilograms, and iron is 7,780 kilograms per meter squared. Now he's also written down the volume of Earth, which is 1.083 times 10 to the 21 meters cubed. Now let's see where he's going with this.
If you use NASA's fact sheet with their mass of Earth, which is 5.9726 times 10 to the 24th kilograms, and you divide that by the volume of Earth, you will get an average density of Earth, I'm going to call that rho E over here, of 5,515 kilograms per meter cubed. Okay? So, looking at this, just looking at water and soil, water is, well, the average density of Earth is over 5 times greater than the density of water. And water is actually pretty dense. If you've ever done a belly flop into a pool, you've seen how you've experienced how dense it is. But the average density of Earth is 5 times that of water. It's also a lot greater than soil and sand, which is really ground rock. But then you look at the density of iron and notice that actually the density of Earth is pretty close to the density of iron, based on everything that was calculated, the mass that came from this relationship up here.
Okay, now genius, we've got 2 quick questions for you. First of all, if you're going to guesstimate a density of the Earth, would you make it a little closer to soil or a little closer to iron? Now, if in reality this was calculated, as it was in reality and continues to be to this day in thousands of episodes every year, we find that the average density of the Earth is much closer to that of iron than it is to stone. Let's put 2 and 2 together here, my friend. what does that tell you about perhaps the core of the Earth? Any suggestions?
So I started thinking, this is pretty high, and that's exactly why we theorize that the Earth has an iron core, because this is the average density of all the stuff in Earth, all of the elements, everything on the periodic table that we know. Now, at the time, they didn't know all the elements on the periodic table, but they knew a lot of things. So what I'm saying here is, if you follow where I'm going with this, how do we know they didn't guess, or that Cavendish didn't guess this mass of Earth, and then just use it to solve for G, and then do the opposite and say that he did this, that he solved for the mass of Earth using that value of G? It's the same thing, just based on the algebra. And then if you plug both of those values into this equation up here and use the mass of any object, whether it's a man, a horse, a carriage, anything, and use the radius of Earth, you're going to get a force that's equal to the weight you get for that same object if you just multiply the mass of that object's time the acceleration due to gravity, or the rate at which the acceleration at which things fall towards Earth.
Okay, I think I've had about enough of that. Now, let's talk about a couple of things here. First of all, how was G determined? I gave you a rough breakdown of the Cavendish experiment in this video. I've got a link to a longer video that I did yesterday that had very specific details about how the Cavendish experiment was done. This related the gravitational force between two lead balls outside of the gravity of the Earth. All right, it's not a guess, it's a measurement. That measurement continues to be made tens of thousands of times since then, coming up with approximately the same number. Now, to suggest, as a professional engineer and somebody who apparently had at least college level physics, that this was a made up number is a lot more than just laziness. This is a lack of integrity. This is a violation of professional ethics. And I am astounded that he would put something like this on video and upload it to YouTube. This is so easily disproven with even a cursory search on YouTube looking for Cavendish experiments. To suggest that this number was just made up to fudge the figures smacks of simply trying to support a narrative. It is a violation of professional ethics, and I'm just shocked. Now, here's what I would suggest people do. Go over to BM Furball Pancake Heroes channel and subscribe to his channel. He is actively doing a Cavendish experiment right now, as I said, using weights, PVC pipe, and piano wire. He's been working on it for some time now, and it's being done live stream. You can see that this calculation, or this measurement, is actually something that's real. You can go on YouTube and find dozens of other experiments that do the same thing, and again, come up with a reasonably accurate number for G. So, right now, basically, I have absolutely no respect for this Mr. Mullins. Quite frankly, a structural engineer that, one, doesn't believe in gravity or seems to doubt it, two, thinks it's a made-up number. He designed structures that people's lives depend on. And if he doesn't have a firm grasp of this, he is a danger. So, I'm going to continue to watch this because this is a man's career. But quite frankly, if this continues along this line, I think he needs to be reported to his professional board. Now, that's on me. because I'm the one reviewing this stuff. It's my understanding others have done it before, but if these are still being put out as definitive words from a structural professional engineer, simply to mislead people on the internet and support a narrative, what kind of person is this? And I'm sorry, I find it very upsetting. I wouldn't tolerate this with another physician. I sure as hell am not going to tolerate it with somebody that's building bridges. So, this Bob the Science Guy, I think I've had about enough of this gentleman for one night. I'm going to take a break and maybe look at some of his other videos here at a little bit of a later date, maybe a few days. But I think that what we have here is pretty clear. So, thank you very much for tuning in. Please be sure to like and subscribe to my channel. Yeah, just hit the little button. There's a logo right down in the lower right corner. So, thank you very much for stopping by. We'll be seeing you again soon. Take care, guys.
This rabbit hole's too deep for me.